the problem now, so what we did at the 8 a.m. one was to look at the forward solution. And so what the forward solution is we, at each point in the cortex, we assume each little chunk of the cortex has some current, current either flowing sort of perpendicular to the cortical surface, toward the cortical surface, or down away from the cortical surface. And the basis for that was the current source density measurements that show that sources and sinks vary very rapidly as you go through the cortex, perpendicular to the cortex, and much less rapidly when you go sort of parallel to the cortical surface. And so the forward solution is, let's make a model of the head that's got some brain in it that has a certain amount of conductivity and certain permeability to magnetic fields, and then we'll essentially make a model for a given amount of current perpendicular to the cortex at a particular point, pointing in a certain direction. What do we expect the voltages we would measure at each point across the scalp, or magnetic field direction, strength and direction, that we would measure across the scalp? So that's the electric and the magnetic forward solution that basically just describe a bunch of weights between each pair of sources and sensor. So you got a whole bunch of sensors, well, not a whole bunch, you got a couple hundred sensors, you got maybe 10,000 sources, and so you're going to need a 200 by 10,000 matrix that will tell you what is the weight for each possible source to each possible sensor. So that's the forward solution. And we'll sort of write it out as just a simple matrix equation. But what we really want to know is, we recorded a bunch of stuff outside there, and where was it coming from? And so that's the topic for today, the inverse problem. So how do you sort of figure out where sources are, given a model of how current dipoles generate data on the scalp? So how do you invert the forward solution? And the major sort of structure of the forward solution is something that's close to an inverse square. And so what this means is, as you move away from as the source moves away from the sensor, the visibility of the signal goes down very rapidly. So if you have a source that's near the skull, you can see it quite easily. If it's a deeper source, especially if it's a couple centimeters away, it's nearly impossible to see because the effect that it has on the sensor is so small. And because of that fundamental sort of inverse square structure of the forward solution, both the EEG and the MEG forward solution, this creates a whole bunch of problems for us, and especially with regard to sources that are a little deeper. And so in the end, we'll talk about one of many different methods for trying to sort of view our inverse solution that is more informative. So it's noise normalization. So let's start off, just back up a little bit and just say, why localize in the first place? Because if you know anybody that studies EEGs, most of them don't localize. And what do they do instead? They look at temporal components. And partly this is kind of historical because initially people were able to record a lot of points in time in EEG, but not very many electrodes because it was expensive to have a lot of amplifiers. So what are temporal components? This is mostly what you see in the EEG literature. Basically what you'll see is you'll do some kind of stimulus 20 or 30 times, and so here's the event. And then you'll average like 20 or 30 copies of that. And then what you'll get is, some kind of ERP wave out of that, out of one electrode. So this is from one electrode. what do people do with this data? Well, they look at the main sort of inflections in the data. So this would be like our N1. And then they sort of treat that like an actual mechanism of some kind. So here's like, here's like a P2, part of the wave. And you vary the stimulus conditions and show how that will sort of like vary the amplitude of a particular component. And so you imagine you're sort of building together these components. Now, what's wrong with that? What's wrong with that way of thinking? Fundamentally wrong with that way of thinking. The problem is, if you go into the cortex and record evoked potentials, all areas look like that. All cortical areas have the same thing going on. And so the first, critical thing is the, response in every area extended in time. So that's and all areas are multiphasic. Positive and negative. So all areas look like that. They go up and down 2 or 3 times. And they're all extended in time, and they all overlap. But what's the worst part of looking at temporal components? So the worst part of looking at temporal components is that they're temporally non-static. And what does this mean? Just take the retina, for instance. So if I just change the brightness of a stimulus and do an evoked potential, I can vary the temporal structure by like 50 milliseconds easily if I just change the brightness or the contrast of a stimulus. If I go into, say, invasively into V1, I can see that there are cells that respond to low contrast that have a higher a quicker response than cells that respond to higher contrast. And so varying the contrast is going to completely change the temporal structure. So these temporal components, like the N1, are not static. They're varied by all different things, including something as simple as just the brightness of the stimulus. So the other thing that this forgets is that basically, one source visible at every electrode. So essentially, no matter where you are in the brain, you're going to see something, if you see something at all, at every electrode. If you're deep in the brain, you're going to see almost nothing at every electrode. But if you're someplace that can generate a signal at one electrode, you're going to see it at all the other electrodes. So what's actually going on from just actually doing evoked potentials, local field potential recording inside the brain? Well, we know what's going on, So here's V1. So if you do a stimulus in V1, you might see something like that. It's pretty prompt. It's a little bit faster than the response in V2. So V1 sort of happens if this is where our stimulus was starting. So there's a little bit of a delay in V2. If you go to an area like V4, there's even a little bit more of a delay. But if you go to an area like MT, since MT gets a lot of input from these large cells that have a lower latency, you can see the MT response is going to be just about as fast as V1. If we go to dorsolateral prefrontal cortex, that's an area that receives from MT. It's actually going to be, so it's a higher level processing, but it's actually going to be faster because it received from MT, it's going to be faster in its response than V4, which is an earlier processing stage. And if you go to inferotemporal cortex, I have some readings that you can see of like what it looks like to record evoked potentials from all these different processing stages in the cortex. So if you go to inferotemporal cortex, that has a little bit more of a laggardly response. But frontal areas can be faster than posterior areas that are nominally sort of higher in processing. And what do you see at one electrode? Well, you just see the sum of all these. So just add all those together, and that's what you get up there. So what's wrong with that? What's wrong with sort of like taking that summed thing across all these extended signals coming from all these areas and then like breaking it down into temporal components? Those are not components. They're just some kind of addition of all these little spikes on top of each other. And when you move them around by sort of fiddling with how all these different areas are interacting, it's not the right way to do it. So what's the right way to do it? Well, the right way to do it, so by contrast, the spatial structure of the scalp recordings of EEG or MEG. So the spatial structure of a scalp recording, from one cortical location is static. So if any part of the cortex becomes active, it will always have a fixed spatial distribution on the cortex, unlike these temporal components, which you can just go all over the place depending on how you varied the mix of cortical areas that were involved in generating the evoked potential. So these are much better components, some kind of spatial components that are fixed in their spatial distribution when a particular part of the cortex becomes active. You can guarantee. Now, you're going to have trouble seeing deep things, but these guys have trouble seeing deep things too. So that's really the fundamental reason to localize, is that you're dividing up your signal into things that correspond to different actual parts of the brain. Okay, so how can we do that? Well, let's first write out our linear forward solution, which is linear if you assume that you've got fixed sources. So if the sources are all fixed in their position, then you'll end up with a linear forward solution. So here's our forward solution. And you'll see this written in all different ways. You can write it out as just like a sum. So here's our forward solution for one source, I. So we'll have I for sources and J. I for sensors and source and J for sources. So basically our forward solution says it's just a linear sum, across all of the sources of just a weighted sum of the amplitude at each position in the cortex. So here's our weight. That's our forward solution, basically. So what is that thing? That's the thing that we talked about, in the last. It's like the strength of the local dipole, and that's what the orientation of the dipole is, and then that's the vector to our recording site, and then the whole thing is divided by the vector to the recording site, the length of the vector to the recording site cubed, and then, plus we've got some corrections for the fact that the brain is not infinitely large. Those are smaller corrections. This is the kind of like the basic forward solution. And what does that thing generate? It generates a number. It's just a single number that just says, for a given source, J, what number are we going to multiply that by to add into this sum that will generate our signal? And then there'll also be some noise. So here's, and that's by sensor. So let's just label all these things. So this is sensors. Unfortunately, sensor and source is the same letter. So this is source. So J is source. This guy is, the forward solution. This guy is, the dipole strength. And this is the noise, sensor noise. So the linear part means that we can just sum. So, so for a given sensor, it's just the sum of all the sources multiplied by their weights. So it's very simple, mathematically very simple. So if we write this out as a matrix equation, so again, in the interest of mathematics, we're always trying to get rid of as many numbers as possible, reduce it to the smallest number of letters. But before we do that, let's just actually sort of like see just how many numbers are involved in this. So this thing has got two indices. That means it's the forward solution is a matrix. And so if we write that out, we've got a vector. So that's only got one index, so that's a vector. So we'll say a vector of electrical recording. We'll start off with electrical recording, EEG recording. So that's going to be equal to this very long rectangular matrix. I didn't draw it as long as it should be. It should be like 10,000 long and only about 200 this way. And so this direction is sensors. So sensors, so that's a number of voltage measurement at every sensor. And so this is also sensors. And then what's this direction? This direction is sources. A lot more of those. And so in this matrix, what are the pieces of this matrix? Well, if we look at a column of this matrix, what is the column of that matrix? Column, it's basically the weights. It's the weights for one source. One source. So those are the forward solution weights for one source. And if we look at a row in this matrix, it's the forward solution weights for one sensor. So this is forward weights for one sensor. There's a lot more of those because we've got 10,000 sources, and so we need 10,000 numbers going to one sensor. Okay, and so this guy we'll call the E matrix. So that's our electrical forward solution matrix. And then we're going to be multiplying by a long vector. So there's going to be a vector like that long, and those are our sources. And I didn't draw it long enough, because like I said, it's got to be, there's 10,000 of those. So this guy's our source vector, and then we've added on some noise. And the noise is going to be the same size as the sensors. This is sensor noise. This is noise, electrical sensor noise. So there might be some, just some additional stuff that's not coming from the brain in our signal. So how do we add? So this was for electrical sensors. So this is EEG. How do we add the MEG? We just tack on some more data here. So there's going to be another set of we'll call those guys M. So that's some magnetic data, and that magnetic data is going to have to have a magnetic forward solution. So we'll tack on a magnetic forward solution onto that guy, and so that's we'll call that our B matrix. So that's the same thing, except for we have the cross product here, instead of the dot product in our forward solution. It's still an inverse square kind of thing going on. And then we're going to have to tack on some, let me make sure that this one is clearly bigger. That one's clearly bigger. We're going to have to tack on some magnetic sensor noise. So here's some noise, magnetic. Or how about make it B, noise magnetic. Okay, so that's our forward solution. And how can we sort of summarize this down to even fewer letters? So basically, it's just a vector of measurements equals this giant rectangular matrix of electric and magnetic forward solution, just times a vector, which will give us another vector. And then we add some noise to that vector. So this is, sensor noise. Here's our, forward. That includes, E and also B. Here's our source strengths. And this is our data. So that's just a simple linear equation. We take whatever the unknown source strengths were, multiply them by this forward solution that tells you the weights for each source sensor pair, add some noise to it, and then that gives us our data. And it's a linear because we've assumed the dipoles are fixed. And that wouldn't be the case if we were trying to, say, fit a dipole by adjusting the dipole until its forward solution looked like our data. That's not a linear problem, but this one is. So that's the good part of it. It's linear. And then what's the bad part of it? Well, there's way too many unknowns. So you can see, this is sources going down in this case. And, what is that? That's going to be like about 10,000, okay? And then how much data are we going to have? Well, we might have, say, 250 MEG detectors and, say, on a good day, like 128. So we got like about 300 here. So this guy there's 300 of those and 10,000 of these. And what's the problem? Well, these are the unknowns. And so we clearly have an underdetermined problem. There's other problems with this problem that even if we had exactly the same number of knowns as unknowns, we would still have some problems. But there's like sort of secondary problems, alternate solutions that give you the same result. But if we just, for the time being, concentrate on the fact that we got not anywhere near enough data to solve for all these guys, how are we going to solve that problem? It's an underdetermined problem. And so the way we solve for that problem is we add some data. And so what is the form of adding that data? It's basically some simple assumptions about what the variance and the covariance of the different sensor noise and sources are. So we can just add in some assumptions about what the variance of these guys are, or the variance of these guys are, and we'll show how to add them in a way that's very sort of non-committal. And if we do that, then we can have enough information to solve for S. So these are unknowns. We want to solve for S. So how do we solve for S? So we solve for S by basically just inverting this equation. So we just want to solve for this guy. So how do we solve for that guy? We solve for that guy by just coming up with a matrix that when we multiply the data times that. So here we've got the sources times the matrix. What we want is we want the inverse matrix, which is we take the data and multiply it by a matrix, and then that gives us the sources. And so basically our inverse solution, I'll sort of draw out what it looks like sort of in a matrix over here. So let's put a dividing line because that was the forward. Okay, so this is forward going this way and inverse going this way. Okay, so what is our inverse solution? Our inverse solution is basically just, here's our source vector, 10,000 long, and we want to basically just find a matrix that when we multiply it by our data vector, this x vector, we get our sources. So you can see what the problem is. So we've got a couple hundred of these, and we're solving for 10,000 of these. So what does that matrix look like? Well, that matrix looks like, that matrix equation looks like a really long set of source amplitudes here, and it's going to equal this extremely elongated matrix. This is the W matrix. That's our solution. That's our inverse solution. And then that's going to be multiplied by something that's that big. So here's our data. So this is our x data. And so what is one row here? So one row here, this would be the forward solution for every source. So this would be for every sensor. So one row there is going to relate for a given source somewhere down in there. What is the forward solution for every sensor across the head? So there's going to be less of those than the other way around, which would be the forward solution for every source. Sorry, misspoke. Okay, so that's the forward solution for every sensor there. It's the inverse, not the forward solution, it's the inverse solution. Finally got it right. Okay, so inverse solution for every sensor. And basically when we do that matrix multiplication, we take our data and just multiply it by this fixed matrix for every time point. So this is just a single time point of data, single time point, important point of data. And then this is, fixed for all time. Fixed for all time, because that doesn't change over time. So this guy's a single time point of data, fixed for all time. And then we get, these thousands of numbers for every source. So if you look in the notes, there's like pages of matrix algebra, but let's just write out the equation for this inverse solution. And so that equation is, here's our inverse solution matrix, and it basically just equals some additional matrices which we haven't defined yet. So that matrix we defined, that was the forward solution, this forward solution matrix here that we calculate by figuring out the shape of the head and how far away the sensors are from each dipole. So that's just a bunch of weights. And here it is again. So we're hundreds of thousands of numbers. And then there's the R again. We haven't defined what the R is. And then here we're multiplying by the transpose of the forward solution matrix again. And then we've got another matrix here, C. We haven't defined that one yet. And then that whole thing is inverted. So this is how we calculate. So it's just a linear operation, but this is how we calculate this inverse solution matrix that allows us to sort of multiply any data point in order to get where all the sources are. So now the question comes, where do we get all those extra numbers from? And we get all the extra numbers from several additional matrices. And so the C matrix, here, it's a small matrix that has sensors by sensors. So this is sensors by sensors. And it's the covariance of the variance and covariance of the sensor noise. So this guy is our C matrix. Okay, so each one of those guys. So this guy is a rectangular matrix. That guy's a rectangular matrix in the opposite way. That one was a rectangular matrix reformatted to be sort of long that way. And so all these guys are matrices. So we're talking hundreds of thousands of numbers there. I'll take those off. So we kind of get in the way. So what are the additional things that we added in order to make this problem solvable? Because in this state, when we first look at it, we say we can't solve this problem. It's underdetermined because there's an infinite number of solutions because we've only got 300 data points and 10,000 unknowns. And so we're adding in this information. But what is this information? It's relatively benign information. And so this is the assumed variance along the diagonal of the sensor noise. And what's the simplest thing we can assume? Well, just assume that there's all the different sensors have the same noise. We could actually try to measure it. We could actually sort of like leave the head out and then just collect some data and see are any of the sensors generate more noise than other sensors. So it's possible to actually try to measure that data also, because you might have a noisy sensor on some day. So that's our assumed variance of the noise of the sensor. And then what's the off diagonal? The off diagonal is the covariance. So is there any tendency of two sensors to have spurious correlation that not related to the data? So what can we assume for that? Well, we can just assume that's 0. We could try to measure it also, but let's just, the simplest assumption, just assume that so this is, this is the covariance of sensors. And like I said, you could actually measure that, or you could try to measure it with, in the electrical case, it's a little harder because you would need to get like sort of a fake head that didn't have a brain in it, and then put the electrodes on and then see like, do these electrodes tend to be spuriously correlated more than some other pair of electrodes. So that's the first piece of information that we've added in, a pile of numbers that we've added in to make this solvable. And the second set is a much bigger matrix, and this much bigger matrix is the assumed variance and covariance of the sources. So let's make this, it's much bigger than this even, but so what's down the diagonal of this? So down the diagonal of this is the assumed variance of the sources. Now these are the ones we're trying to solve for. So this is that R matrix. And so so basically this is assumed. Now we might have some information about this, like maybe we did some fMRI and we know that certain of these sources are more active than others. So we might know that, like in this part of the brain, we got some fMRI signal there, and so we know that that part of the brain had more variance in it than some other part of the brain. And we also might have information about the covariance. So this is, assumed covariance. And what is that? That means we might have collected some resting state data that looks at correlations between different parts of the brain. We might know that too, of sources. So this is, assumed, covariance of sources on the off the diagonal. This is a symmetric matrix. So, like, if source 2 is correlated with source 8, well, then we would expect source 2 to be, correlated with source 8. So a number here is going to be the same thing as a number here. Those will be equal. So it's a symmetric matrix. So what's the easiest thing we could do here if we didn't have any fMRI data? Just assume that nobody's correlated with anybody else, and everybody has the same, assume same small. So we don't bias, assume same small. So we could, assume variance noise, we could assume these guys are same small. And those guys we just assume are 0. So that sort of seems like a relatively painless stuff to have added in order to make this invertible so that we can, solve for this W. And so this solution is called the minimum norm solution. So this guy is called, let me just make one more diagram of this guy. What is this? What is that thing? So what that thing represents is basically for one source. So for one source, what is the weight for each sensor? So here's our sensors. So for a single source, what is our inverse weight, our inverse solution weight, which is different than the forward solution. So for each sensor. Okay, so what is this kind of a solution called? So this solution is called a minimum norm solution. And So what is the minimum norm solution? How did it sort of solve the problem of this impossibly large number of unknowns? It solves the problem by saying, let's find the solution with the smallest norm. So it's like find S with smallest norm. And so what is the norm? Well, the norm is just, what we write out like that. It's just the length of the vector, the Euclidean length of the vector. And so what is the norm in just 2 dimensions? So this would be source strength number 1, and this would be, source strength number 2. And so what is the norm of this? The norm of this is just that, the Euclidean distance. So this source strength is just a number. Source strength 1, source strength 2 is a number. Source strength 10,040, that's a number. We just essentially find the length of that vector, the Euclidean length. So this is just Euclidean length. That's the norm. So Euclidean length of that vector, of a solution vector, we find the smallest one, because there's a zillion ones that would work here, but by making these assumptions here, the kind of geometrical meaning of that is find the solution that has the smallest norm. And what does that mean? That means like find the solution that is a legal solution. It generates the actual data. It generates the actual data that we recorded, and it generates the smallest amount of data. And kind of the rationale for that, it seems like, why would you want to do that? Well, as you go deeper in the brain, what happens is it's harder and harder to see the effect of a source. And so it kind of makes sense that what we should do is and so it's going to be easier and easier for things to fall into the noise as you go deeper into the brain. And so it makes sense to try to find a solution that has the smallest overall amplitude. That's kind of what this is, the Euclidean length. What is the overall amplitude of your solution? So try to find the one that has the smallest overall amplitude, which would be the most likely to be right and the least likely to have fallen into the noise, especially as you go deeper. So what's the problem with this? So it's kind of the correct thing. So let's just do a very simple modeling study of how the minimum norm solution works and sort of seemingly fails. So if we take a superficial source, so here's a superficial source. And this is just a modeling study. So what we can do is we can scan somebody's brain, figure out their forward solution, find out where the outer part of the cortex, outer part of the skull, outer part of the skin, do, say, some kind of improved forward solution, like a boundary element solution. So we've got our forward solution. And then do this thing to it, solve, make our assumptions about, covariance of sensor noise and source noise, do this solution, and then just see how it works. And so since we've calculated the forward solution, we can actually insert a dipole and actually calculate what the actual forward solution data is going to be, and then apply this thing and then see what it got back. So it's just a modeling study. So if we start off, so here's a spherical head, and here's our solution. So we start off with our forward solution. So we'll put a dipole here, a dipole, say, like, right near the surface, and then calculate the forward solution. So here's our forward solution. just using this equation and our particular person's head, and then do our inverse. So calculate the inverse, and take that data that we calculated, run it through the inverse. So let me put it up here. So run that data that we just calculated through the inverse and just see what does the inverse solution tell us where the sources are. We know where the sources was. We put it here, but like where did it end up after we ran it through the inverse? And so what is the answer? Well, it works pretty well. There'll be a good-sized dipole here. They'll smear it out a little bit to nearby points on the cortex, but it works well. So that's a superficial source. That seems to work. And there's some uncertainty about exactly where it is, but that's okay. So the minimum norm will give you, this will be the solution that has the smallest norm. Now, what happens if we take a deep source and just do the same thing? So why did this work in the first place? Well, we're near the surface, and because of this inverse square relationship, we've got a nice big signal for a piece of the cortex that's near the surface. So here, let me draw that little piece of cortex in there. So here's a piece of cortex in there like that. So that was a piece of cortex that was near the surface. And so, what's going to happen is that it's going to mostly put those dipoles in the right place. Okay, so what about if we've got a deeper source? So now what's going to happen? Say our source is the same size source. So here's that source. Let's put that source down here. And say that guy is at the bottom of a, something like that. It's the bottom of the sulcus. Not very far away, centimeter or two. And so now what happens when we calculate the forward solution? We'll get a little teeny tiny forward solution because of the inverse square. Spread out forward solution, something like that. And why is it so small? So let me make that guy a little thicker. So here's the cortex. Here's the outer part. So this guy is the forward. It's really tiny. And why is it tiny? Tiny because inverse square. Because that's just the way it is. You're much further away from the sensors. So now what happens when we try to solve for where? So just take that forward solution. Take this forward solution, this guy, and run it through the inverse. Run it through the W, and just see where take that data, this is artificial data we created, run it through the inverse, and then just see where it ends up. And so what happens? Well, you end up with a whole bunch of little guys right up at the surface. Like that. And so why do they end up at the surface? So, and it turns out there's a little teeny guy down here, even smaller than those other guys. So why didn't we get this? And so the reason we didn't get this is because the norm of this solution is smaller. So the reason that it displaces it to the surface is that the norm of surface solution smaller than just this one guy here. So I didn't draw everything to scale, but the bottom line is this single large dipole there has a larger length to it than the sum of all these guys, the Euclidean, the Euclidean length of all these guys. And how could that be? Well, that's because of the inverse square. Because this guy, because you can get away with real teeny tiny guys up here because their forward solution is big. So the forward solution of these guys is quite big, meaning for a small amount of dipole source, you can get a big output on your forward solution. Whereas this guy, even though he's quite big, he makes a really tiny forward solution. So when people first saw this, they were sort of unhappy. They said, I don't like it. It's discriminating against deep dipoles. And why is that? Well, they should be discriminated against because they're harder to see, because they fall into the noise much quicker because their forward solution is very small. So this is kind of the rational thing to do. So what do people say? Well, we've got to give the deeper dipoles a chance. So like early in the localization, people said, why don't we just turn up the variance, the assumed variance of the deep sources? And if you do that, that will fix this problem. You just turn up the variance of the deep sources, then some deep sources will appear. What's the problem with that? Well, if you just start off with noise for your data, if you just start off with noise for your data, what are you going to get? Deep sources. Why is that? Well, because you put a prior probability, prior expectation that there's going to be more active deep sources. So obviously that can't fix the problem. So there's a variety of things that people did to try to sort of get around this. But one simple way to sort of to not get around it is just to essentially normalize your solution for your viewing pleasure by, we'll call this, noise normalization. And so there's the paper if you want to read about this by, Anders Dale, my former student, noise normalization. And this is basically just a way of viewing the solution. So if we go back to the solution right here, if you look at the actual place where the dipole was, there's a teeny tiny dipole there. It's even smaller than the ones at the surface. It's even smaller than these guys up here. But there's a little one in the correct place because there's a possibility, even though, it's a deep source and makes a very small signal that's barely above the noise, there's still a chance that it's there because it lines up with this. It could have generated this forward solution. And if you look off to the side, there's almost nothing there. These guys are pointing in different directions, and so their forward solution wouldn't look at all like the actual forward solution that we got by sort of modeling what this slightly raised, spread out thing would look like. And so the question is there some way we can, so if anything appears deep, it's very significant because it's so hard to see it. And so the noise normalization is just a way of kind of viewing, it's kind of like more like a stat, like sort of viewing your solution. Your solution is still a minimum norm, mostly displaced to the surface, but we're going to view it to sort of see, did anything appear down there? Because if anything did, it's pretty significant because it's so hard to see stuff down there. And so how do you do this? It's just trivially simple, very, very simple. And what you do is you just divide by the norm. So in the tradition of sort of mathematical economy, what does it mean to put a subscript on a matrix? So what a subscript on a matrix is basically just get all the numbers in the matrix that are in one row. So if I are the rows and j are the columns, what does that symbol mean? It means like just get the vector that's the vector of forward solution numbers. It's this the inverse solution numbers. It's the inverse for every sensor. And then basically do something to them. And what are we going to do to them? We'll just divide them by their norm. So here's that row, and if we take the what does that mean? That means just take the Euclidean distance of that inverse solution. So, and that will give us a new W matrix, and this W matrix, it's I noise normalized. And so all we did is we divided every number in that row by the norm, by the Euclidean length of that inverse solution. And so what will happen? Well, and so what will that sort of do to your, I knew I had one more page somewhere in here. Yeah, so what will that do to your, let's erase this guy over here. So how will that fix things? So we can do the same kind of modeling study that we did last time, except now use our noise-normalized inverse. And so what's going to happen is if we, so say this is the insula where you have some deep sources. So if we start off with a superficial source, so this is noise normalized W modeling. So this isn't real data. What you do is you just start with a superficial source, calculate the forward solution, and then do the inverse. So calculate that forward solution and then do the inverse, with the W, multiply by W. And then just see what you get. And so what do you get? It's going to smear out the forward solution a little bit. So here's where it would have been if we had just done the minimum norm. So this guy is, noise normalized. And this guy is, original minimum norm. So it's going to slightly punish superficial dipoles. But what will happen with a deep dipole? So if we have a deep dipole, say somewhere in the insula, so if we put a dipole down there, it's just a couple centimeters deep, not very deep. What's going to happen? Well, we'll get this horribly spread out, very small solution like that. And then when we invert that guy, what's going to happen? So if we just looked at the original minimum norm solution, it's going to displace that all the way up to the surface. So you'll get this sort of ring around the upper part of the insula that's closer to the surface. And what happens, so this guy is, original minimum norm. And then, what will happen if we use the noise normalized one? It will sort of more or less be, it'll smear it out a lot, but it'll more or less be in the right place. And why did it help? It helped because we divided by a small number here. So here's the real inverse solution. The real inverse solution says, it's really hard to see anything down deep. So, this number is going to be pretty small. But when we take the norm of that whole row to sort of get what's the strength of the inverse solution for that point. Take the norm of it, that's the strength of it, and then divide by that, that's going to be a small number, and so then that's going to make our noise normalized number bigger. And so what's going on is it says, like, I found a little tiny thing down there, but since that's so hard to see, also known as having a very small sort of inverse solution, because its forward solution is so small, because that's very hard to see, it falls into the noise, it's really significant. And so I'm going to sort of, divide it by a small number and make it bigger. So this is, only for viewing pleasure, right? It's not the solution. It's not the solution. So the minimum norm is still the solution. Is still solution, but it's a way of kind of looking more like a stat at your data. And so what is the, what's the bottom line? Why should people do this? So it's, if you've stuck with it so far, it's kind of, there's so many twists and turns. But why should you do this as opposed to just doing components of ERPs? And the reason you should do this is because this kind of localization of activity in the brain, it's not anywhere near as good as fMRI. It's not anywhere near as good as fMRI. But what can it do? So, what are the problems? So, deep, hard to see. You're going to be biased against seeing deep sources. But on the positive side, you can localize patches that are, say, 1 to 2 centimeters, across, and say less than 1.5 centimeters deep. Okay, so what does that give us? Well, compared to fMRI, it's real data, it's actual sort of sources going up and down in the cortex. And so you can tell, like, say some posterior areas like V1 and V2 apart from, say, areas around MT that are a little higher. And you can tell sort of like middle infratemporal cortex from anterior infratemporal, although it's kind of a little hard to tell it from the frontal operculum because those things are very close to each other. You can tell, dorsolateral frontal cortex, dorsolateral prefrontal cortex apart from the frontal eye fields, and you can tell like the foot apart from the hand, apart from the face, and you can see sort of, anterior parietal, and you can tell that apart from sort of posterior parietal, and you can tell that apart from the angular gyrus, and you can tell that from all the auditory areas, they kind of get squished into. That you could probably tell some of these more anterior auditory areas, and you could see a little bit of orbitofrontal cortex versus like anterior dorsal frontal cortex. So you got about 10 or 20 spots in the brain in each hemisphere. And in comparison to doing components, what you're doing is you're seeing like this is actually, I'm looking at a sort of an actual real component is this part of the brain was active at this point in time. And I can also see like this part of the brain was active at the same time as V1 was active. Or maybe V1 got active a little bit later in time because some feedback came into it and it did some processing. That's much harder to see with doing things with temporal components because you're always biased to assume like things later in the signal are going to be coming from higher level areas, but they're not. A lot of times, maybe some signals came back to V1 and did some processing there. So the bottom line is it's not anywhere near as spatially resolved as fMRI, but on the positive side, it's the real deal. It's the actual sort of activity of these, combined activity of a couple of cortical areas. It's not as small as a cortical area. These are, these patches, are bigger than, one cortical area, unfortunately. It's just the way it is. And, you know, if anything's more than like 1.5 centimeters deep, you're not going to be able to see it. But it's a good first pass at the data. And it's well understood how, you know, the solution behaves. The statistics of it are well understood. You're not adding a lot of additional strange information. You're just adding in this very minimal information that you're assuming everything's uncorrelated and everything has equal variance. And then you're just viewing it by normalizing by, you know, how much, you know, by effectively the strength of the noise at each point to essentially allow you to see these tiny little sources down there that are, however, are very significant because they're, you know, they're so hard to see. So it's just a way of sort of, you know, viewing the minimum norm forward solution that's more informative, more informative for a human viewer. And what it will give you, like I said, is, you know, a couple centimeter patches of the brain that are becoming active, possibly simultaneously over time. And this is, more people should be doing this than sort of messing around with components, because this will, you know, it reflects actual sources coming from real cortical areas, not these temporally non-static temporal components. Okay, I went quite a bit over, but so any questions about the inverse? And there's, if you go and read the literature, you'll find many more complicated schemes than this. For, let's assume our sources have to be extended in space. Let's assume the sources have to have a certain size. Let's try to build in, you know, constraints on, you know, what angle the sources are at, or build in mapping data, build in, you know, actual measurements of the covariance of the sources. There's a whole bunch of other different ways of look for sparse solutions that sort of, you know, aren't spread out a lot. There's hundreds and hundreds of different ways of hacking this, but I think it's, what I went through was just the most basic sort of linear forward solution, and then a linear inverse with very minimal assumptions. And there's a good argument that everybody should just do this as a baseline, so you can see like what the data basically looks like, and then you can sort of do more fancy things that, you know, give you more localized solutions. Okay. So any questions about the inverse? So it's the minimum norm inverse. Or any questions that go back to the forward solution. So how we calculate the forward solution, basically it's an inverse square kind of thing. Oh, good. Yeah, there's some readings on specifically on this this paper and on some of the methods of doing the forward solution, if you want to get into it in more detail. Oh, good. That one little question. Okay, well, I'll let you go. Sorry to go so far over.